Hello, so I just wanted to give a solution video for the challenge problem that I posted yesterday. So the problem tells us that we have a 10-foot long ladder. Okay. Sorry, Tenzin, about the curly brace. So our 10-foot long ladder, it's leaning against a vertical wall. And we don't know what this distance here is. This is x, it's in feet. The wall is vertical, so obviously it's making a right angle with the floor, and then we have some angle theta here, and then they tell us that the angle is the angle between the top of the ladder and the wall, and x is the distance between the bottom of the ladder and the wall. So that's kind of visually what's going on. And they want to know the rate at which this quantity x is changing when theta, our angle, is pi over 3. So what this really means is we want to come up with some kind of equation for x in terms of theta, and then we'll take the derivative of that equation, and that will give us the rate of change. So x, this distance here, we can use kind of right triangle trigonometry, so we know that the sine of this angle here is going to be x over 10. And so if we want to find out, and get x by itself, we just multiply 10 by the sine of theta. So we get that x equals 10 sine theta. And so if we want to know the rate at which x is changing with respect to theta, we do dx d theta, okay? So remember that the derivative, it's not just a slope. It does kind of tell you the instantaneous slope of a graph, but when you're looking at it in the context of a word problem like this, it can represent any kind of rate of change. So when it's just a generic function of y in terms of x, the derivative is the rate at which y is changing with respect to x. But when you have something like this, where you have an equation for x in terms of theta, the derivative is going to be the rate at which x is changing with respect to theta. So if we take the derivative with respect to theta, then we get 10 cosine theta. And if we want to know the rate at which it's changing when theta equals pi over 3, all we have to do is plug pi over 3 into this equation. So dx over d theta equals 10 times the cosine of pi over 3. And remember that the cosine of pi over 3 is 0.5 or a half. Pi over 3 is the same as 60 degrees. So cosine is 60, or cosine pi over 3 is going to be 0.5 times 10 is going to be 5. And the units of that are just going to be whatever the units of x are over whatever the units of theta are. So in this case, it's going to be feet per radian. Okay. But this same kind of idea can be applied to any type of equation. So a real common one that you'll see is if you're given a position equation. So for instance, if you're given a position function, oftentimes it'll be written as s. So if you're given a position function like s equals, say, 2 cosine t plus 3 sine t, you might be asked, for instance, what's the velocity, or what's an equation for the velocity? So velocity is the first derivative of a position function. So remember, we have position in terms of time. So if we take the derivative, we're going to have ds over dt. So we have change in position over change in time, and that's units of velocity or of speed. So this is velocity, a velocity function. And so if we wanted to know what that is, we take the derivative of this term, which is going to be minus 2 sine t. And then we take the derivative of this term, which is going to be plus 3 cosine t. And then from there, you might even be asked, what's the acceleration? Okay, what's the acceleration of the object in terms of time? And again, if we do the derivative of the velocity with respect to time, we have a change in velocity, so that's units of, meters per second or feet per second or whatever, over seconds. So it's feet per second squared or meters per second squared, units of acceleration. So we just take the second derivative. In this case, derivative of this is going to be minus 2 cosine t, and then here we're going to have minus 3 sine t. Okay, so I'm going to be posting a little assignment, kind of like a take-home quiz later today that'll kind of use some of these examples. It'll be a problem kind of similar to this, maybe a couple other problems that are, similar but also a little bit challenging. So look for that. I'll be posting it in Google Classroom later today.